three talks. The first one is about fluid calculation on CH4 and CO2 by Guillermo Román.
Good afternoon. In this talk I want to explain our work in the last year and a half. Our approach to this system, that is water to hydrates, it's in the density functional theory level using CS. Due to the characteristic of the system, the energetic is ruled by van der Waals forces. Van der Waals forces has been historically described in DFT with ad-hoc potential. But we are going to use the full unlimited approach that David Langred and co-workers presented a few years ago. With an efficient implementation we have recently developed. With this implementation, you can study big systems. So this is the outline of the talk. I am not going to explain the method, but I want to give a general overview. I want to spend a few minutes explaining why we are going to study this and what is a water to hydrate. Then we will see some relevant results in this system, and I will finish with some conclusions. So, van der Waals cannot be described, cannot be explained with the most extended approximation of the DFT, like local density approximation, LDA, or general gradient approximation, LDA. And here we have an example. This is a dimer of argon, and we can see that with general gradient approximation, we are very far from the experiment. Indeed, according to this approximation, the dimer of argon doesn't matter. A similar result we have when we use a dimer of benzene, in this case with two different parameterization of the general gradient approximation. And in the case of two layers of graphene, we can see that LDA gives us a small binding, but it's clearly underestimated, and the asymptotic behavior is not the correct one. So the main reason for this is that both local density approximation and general gradient approximation are local and semi-local. And van der Waals is a non-local correlation. In 2004, David Langred and Lindquist groups developed the first functional for general purpose, which include dispersion forces. Now, if we see the dimer of argon, we can see that with this functional we have very good result. It's true that this functional tends to overestimate the relaxation distance. They got very good results in many dimers, in small molecules, in carbon nanotubes, in graphite, in many systems. But all the systems have one common characteristic, is that they are small. And why they are small? Because the functional is very expensive. And why is very expensive? It's very expensive because the non-local correlation energy, which is treated separately to other contributions to the same correlation, is defined as a double integral in the real space. This double integral is the double integral of the electronic density in 2 points, and a universal function which depends on the distance between the points and depends on another universal function. So, in order to study big systems with this functional, a new implementation was made, a cheaper implementation was made. And that implementation is based on two ideas: an appropriate factorization of the universal function, and the use of the fast Fourier transform. With these two things, we can decrease the number of operations from something that goes as n squared to something that goes as n log n. So the point, I'm not going to explain the method, but the main point is that you can rewrite this universal function as the sum of the product of some interpolation functions and the universal function evaluated in some. So if we use that new definition of the universal function and we introduce this in the double integral, we have something like this, where delta is the product of the electronic density and the interpolation functions. So once we are here, we can use the convolution and we can pass from a double integral to a single integral, and the cost of the computational cost is over the fast Fourier transform. So coming back to the test system, we see that our results are exactly equal than the results you can get with the direct evaluation of the double integral. Exactly the same with the liner of benzene. Our results are the solid lines. And in the case of the two layers of graphene, we now can reproduce the van der Waals integrals. I want to say something about what means efficient. So if we put our attention in the extra time we need to use van der Waals instead of general rate approximation, we see that for a small system with two atoms, the diameter of carbon, the increase of time, the time we need is very high. But if we use a big system, in this case a double wall Kira nanotube with 168 atoms, and we see that the overhead is very low. So there is one characteristic of the method that is important, and is that the method doesn't use basis set. So although it was developed for siesta, it can be implemented in other methodologies. Indeed, it has been implemented in plain wave codes like Abinit or quantum espresso, and in projected augmented wave codes like GP8. The system, there are many, of course, this functional and implementation, it has been used in systems where van der Waals is important, like absorption of molecules over surface or metal-organic frameworks materials. So with this, I want to give some ideas on what means water clothate and why we are going to study this. Water clothates are crystal structures in which water molecules interact through H bonds. The H bonds articulate a long-range order and build the unit pair. The structure is stabilized by van der Waals forces between the water molecules and small molecules which are absorbed inside the cavities of the structure. These molecules are noble gases, molecular gases, diatomic molecules, and sometimes bigger hydrocarbons. In my opinion, any system which attracts the interest of multiple disciplines is interesting. So here I give a small list of some disciplines that has studied water clothates. Probably the reason of this interest is because water clothates are very common in nature. Also, the most common molecule, the most common gas molecule is methane. And furthermore, that methane clothate represents the greatest reservoir of methane in the world. Here I give a map in which we can see some known and some inferred deposits in the world, and a table with estimation of the amount of methane that are absorbed in this structure. This table can be contextualized if we say that the estimation of the total hydrocarbons in the world is around 5,000 gigatons. And here we have numbers like 65, 10,000 of 3,000. Of course, there are some pragmatic reasons to study this. One of them is there is not a lot of abinitio work to it. Also, there are some relevant questions, and of course, this system has 3 different interactions, and it's a good system to study this interaction in the same system and using the same tool. So, okay, let's go to the structures. So, according to literature, there are 3 different structures. Structure 1, 2, and 3. These 2 are fluid and this is hexagonal. And all of them are the combination of different cavities. So there is one cavity, the Cabrera 1 or 512, because it has 12 pentagonal faces, that is common to all the structures. So if we combine this cavity with the 512-62, we have structure 1. With the 512-64, we have structure 2. And if we combine this cavity with the other 2 cavities, we have this is the 4-3-5-6-6-3 cavity, and this is 5-12-6-8 cavity. So if we combine these 3, we have structure 8. We are going to focus just in structure 1 and structure 2. Why? Because structure 1 is the most common for methane, and because structure 8 has the biggest heterogeneity of cavities and faces. There is another reason to use structure 8 is because here I show the unit cell of the structure 8, and we can see that it has one cavity that is much more bigger than the other ones. Okay, so let's go to solve some results. Almost all the results I'm going to show have been done with CH4 method. Here I show some precision parameters of the method that I'm not going to explain because I don't have time. But I want to stress that all the results I'm going to present, in all the results I'm going to present, basis set to the precision error has been correct. So, although the structures cannot exist without molecules absorbed inside, we think it's a good starting point. So we look for the lattice parameters of the structures 1 and 8, and we see that the numbers are very close to the experimental ones. So when we put molecules inside, we recalculate the lattice parameters, and we see that the differences are very small. Even when we force the structure to absorb more molecules than the maximum exothermical number of molecules, that is 10, we see that the difference is very important. So we are not going to consider changes in the lattice parameters. The occupation factor of the hydrogen in this system is 0.5, and that means that there are different possibilities of the H-bond network. So what we do is to explore the different possibilities, and we show that the differences in energy are very small, and also the differences in absorption energy are very small. So we are going to take the system with the lowest energy, and we are going to control. We use double zeta polarized optimized phases for the system, but in order to check that the bases were complete enough, we did some calculation with triple zeta polarized. Again, we see that the differences in energy are very small, and for example, we check that the H1 length are exactly. So, water fluorates are metastable phases of the water, because the stable phase is the ice. Here I show the difference of energy among ice, structure 1 and structure 2 in electron volts per molecule. So metastability means that with some thermodynamical conditions and with an occupancy, these systems could be more stable than the mixture between ice and vapor. So we are going to see something about impact. And we are going to calculate the absorption energy for a small molecule. Why these molecules? Because water glacier has been proposed as a good system to store hydrogen, has been also proposed to be a system for carbon dioxide sequestration, and we use methane because it's the most common gas molecule in this system. So here we have a table in which I show the absorption energy for two different treatments of the exchange correlation for both structure and for all the cavities. The first conclusion we can read is that van der Waals governs the absorption and stabilize the structure. Even more, if we don't take into account van der Waals interaction and we use general radial approximation, this structure will exist. The second conclusion we can read, we can see here, is that all these numbers that are the absorption energy in different cavities are more or less equal, except for this cavity that is the biggest one. This is because more or less all the cavities have the same radius, and all the molecules relax in the center of the cavities, except in this case that the molecule relax close to a wall, and that means the molecule doesn't interact with the rest of the cavity or interact less. That is the reason these numbers are slightly low. Another conclusion, if we put our attention in the column labeled with all, that is that again this number, okay, it means that if you have all the cavities in the unit cell occupied step 1 and you put one molecule in the empty one, you have this absorption energy. So again we see this more or less the same, the numbers are very similar, and that means that the interaction between molecules from different cavities is small, and we can consider that interaction a second order there. So we're interested in the maximum occupancy. So structure 1 is not very interesting for this because you only can absorb one molecule per cavity, but structure 8, which has 3 different cavities, in the 2 small ones, again we can only absorb one molecule, but in the biggest one we can play a little bit more. So here I show the absorption energy of 1, 2, etc. Molecules when the rest of the cavities are empty and when the rest of the cavities are occupied. So we can see this number here, and we can see that the second order energy that I have just said, in this case is important and helps to absorb a new carbon dioxide. If we see the biggest cavity with one molecule inside and with 5 molecule absorbers, and this is methane, the first thing that we can see is that the shape of these cavities are very different. So that means that the network, the H1 network, is very flexible. So there is a competition between the energy you gain absorbing one molecule and the energy the H1 network wastes to deform the cavity. So when the second one is bigger than the first one, you have reached the maximum completion. A piece of data that is important is the number of molecules you need to stabilize the structure. In the case of methane and carbon dioxide, it's 2 or 3, and in the case of hydrogen, you need around 6 molecules. We have said at the beginning that bigger hydrocarbons can be absorbed in this structure, and after a complete study, we can say that the biggest hydrocarbon can be absorbed in structure 1 is propane, and in the structure 8, because we have the biggest cavity, every isomeric form of butane can be absorbed inside. So Another important thing is what about the diffusion of the molecules in these structures. We have rejected the diffusion through square faces because the area is very small. And what we are going to do here is, in the biggest cavity, we are going to move the molecule from the center of the cavity to the center of the face. We have realized that it's very important to relax all the structure, not only the molecule or not only the cavity, because otherwise the barrier to get. So we saw that you cannot, the molecules cannot diffuse to pentagonal faces, because when you put the molecule very close to the structure, the Colombian repulsion breaks the H bonds. On the other hand, here I show the energy barriers for diffusion through hexagonal. We can see that methane, the barrier for methane is very high, and that rejects the diffusion of methane in this structure. In the case of carbon dioxide, is lower, but still is a little bit high to ensure that the diffusion is possible. And in the case of hydrogen, the barrier is low and is in a good agreement with quantum chemistry calculations in isolated particles. So the same calculation has been repeated with another method, in this case Nagel-Elastian band method, and in this case has been done with quantum espresso code, and the results are more or less the same. Here we have the result for hydrogen around 0.3, and here we have the result for methane, that is 0.2, 1.2, 1.3, so more or less the same. With this, I think I have finished, and I want to give some conclusion. And the main conclusion is that van der Waals governs the absorption of this system, governs the absorption and stabilizes the system. Another important conclusion is that this system have a high capacity of storage, and one of the reasons of this high capacity is the fact that the H bond network is very flexible. In the diffusion, we have seen that it's not possible the diffusion of methane to the structure, and for carbon dioxide, it's not clear at all. It's not clear at all. That means that there are some authors that have proposed that an in situ substitution of the methane with carbon dioxide. With our numbers, we think that is impossible because the diffusion of methane is not plausible. On the other hand, water plateaus are good candidates for storing molecular hydrogen. I only want to say this is the people who have been involved in this project, Felix Duran, José Soler, and Mohamed Mayer from the Department of Physical Materia Condensada, Elvira Tacho from the University of Cambridge, David Landgren from Rutgers University, and Timo Thorhausen, Brian Cole, and Kimi from Wake Forest University. Thank you.